All right, so hello everyone. My name is Viraj, and today we are going to be discussing the problems from Leetcode Contest Weekly 407. All right, we'll be discussing all four problems. This is the PCD for that. Let us start. All right, so problem one, number of bit changes to make two integers equal. Now, very simple problem, like requires some knowledge about bit manipulation, how you handle bits and everything. So if you are aware of that thing, this might be a very easy question for you. Also, like otherwise this might not be a very easy question for beginners, so you can maybe pause the video here, learn about basic bit handling. I'll be discussing that definitely in the code part and everything, but let's try to quickly see this question. So the name of this question is very uh, obvious what we are trying to find also. So they are saying you will be given two positive integers n and k, and you can choose any bit in the binary representation of n that is equal to 1 and change it to 0. That's all you can do actually. You will have to return the number of changes needed to make n equal to k. If it is impossible, return -1. Let's try to see how is it impossible, when is it impossible, what will happen, and so on. All right, so let's say the numbers are 13 and 4. Then the binary representation looks like this. I'll just take this into consideration. So let me change my page. So n in binary representation, let's say, is 1 1 0 and 1, and then I have been given that k would be equal to 0 1 0 0. So I can see that I have some discrepancy in bits. I know this bit is not same, this special bit is not same. So I'll say, all right, let me change this special bit, and this becomes 1 now. So my operation count increases, and this bit now turns to 0. This bit is still 0 because they are same. These two bits are still same, don't need to any change. And this bit is 1, wants to be a 0. So I'll convert this to 0, and I have a operation that gets involved, and now I have two operations done. So in two operations, I was able to convert n into k. So I know that the answer is 2. Now similarly, when do you say the answer is -1? Let's say 13 and 14 and 13. So 14 in binary representation should be, I think, 8 and 6. So that would be, so let's say n would be, in this case, you will have 8, and then you will have 4, and then you will have 2. And this would be a 0. So this is 1 1 1 0. This is actually 14. And what about 13? 13 can be represented as, I know I want a 8, 4, and then 0 and 1. This is 13. Now in this case, you have a -1 answer. Why? Because we know that when we want to convert n into k, the only operation allowed for you is convert this 1 into a 0. That's all you can do. You cannot do vice versa. If there is a 0, you cannot convert it to 1 if you want. So in this case, we can see that this 1 and this 0 don't match. I'll change my pen. You'll see this 1 and this 0 don't match. So you can say, yes, if it doesn't match, fine, make this a 0. But when this bit and this bit also do not match, where in this case this is a 0, I cannot convert the 0 to a 1. Cannot do this. And because I cannot do this, I know the answer turns out to be -1. So I hope this logic should be clear, that when we are saying answer is -1, and when we want to say that, yeah, this change is possible, let's do that. So bifurcating every case, it can be simply written as, if bits are same, move on. That is, if we are standing at some ith bit and that bit turns out to be same both in n and k, then you will say, yeah, move on. I don't need to consider or even bother for this bit because it's same. But if the bits are unequal, if bits are not same, then I have two cases. One case is if that bit in n is 1 and if that bit in k is 0, then I'll say, yeah, good to go. Convert this 1 to a 0 and increment C++. Let's say that's the count of operation. But if n bit is 0 and that same bit in k is 1, then say return -1 right and right here, because I know I don't want to calculate the number of operations from now. I know that I received a condition where change was not possible. And if change was not possible, how will I ever make n equal to k? Alright, so this is the whole idea behind the problem. We'll just try to figure this, like, logic out this code into bit manipulation, right? So now how would you tackle each and every bit at a single time? Now a classic method to do is we run a while loop where I can pass both n greater than 0 and k greater than 0. So first I'll try to exhaust both numbers having whatever bits they can from the LSB side. LSB is the least significant bit, that's from the right hand side. So when I do this in the while loop, what I can do is I can say, I will try to, let's say if this was the n number, if this was the k number, so I'll try to exhaust the bits one time from the LSB. Then move on these two bits comparison, then these two bits comparison, then these two bits comparison. Why have I done this? We'll see in a time. We'll see that if I do this something like this, then what can happen is till some bits are present in k and n and both are comparable in nature, I can have a very straightforward logic. I can say that is the bit in n and k currently at the LSB equal or not. So how do I calculate what bit am I standing at and the LSB? There are like basic 2-3 methods to do that. One very simple method is you can simply check if the last bit in the number is turned on, then the number has to be an odd number. Yes, because if let's say there is a number that looks like this, there are some 1 0 1 0 so on some bits, and the last bit is turned on 1, so you know that this bit's value is actually 1. Above this, every bit's value is actually 2 power something I. So adding 2 power I to your number increases your number but only keeps it even. But this 1, when it 1 comes into picture and you also add that into your number turns out to be odd. So one very basic technique to check whether what is the nature of LSB is, you can check whether the number is odd in nature or not. So I'll say is n mod 2 not equal to k mod 2. If that is the case, then I know their last bits don't match. Means either n's last bit is 1 and k's last bit is 0, or n's last bit is 0 and k's last bit is 1. So if this is the case, then I want to do something, because if this is not the case, then I will continue. So I am not even taking that consideration. If both the last bits don't match, do something. Do what? Simply say that is the n bit which I'm talking about equal to 0. If this n bit is equal to 0, then I'm standing at this case where I know if n and k bits last don't match and the last bit of n was 0, that means k bit was 1. Can I convert a 0 to 1? I don't have the power. So I'll say return -1. It's direct, straightforward. And if that is not the case, then I'll say C++. That's the count of operation plus plus, because that means I know I am somewhat incrementing my count of operation there, because I know that in that case, n's last bit was 1 and k's last bit was 0. Definitely that means the conversion is required for me to make n equals to k, and yes, I have been given that operation count power to do that. Let me increase my operations. And this is going to be the first part of the logic. Now when you exit this while loop, two things will happen. Either there will be some n already left, or there would be some k already left, or both n and k are exhausted. There can be like 2 or 3 cases only, right? Because the while loop is saying till n and greater than 0 and k and greater than 0. Both cases, right? If anyone turns false, you say, all right, let me come out of the while loop. So again, I don't want to go into the very depth of how I am implementing this and force this on you. People who are watching this video, they must be aware that normally you are trying to handle bits. Your target is somehow you are able to cover these cases. That's all. If this up till this part was a main discussion of the problem logic, from here whatever is there is just implementation, and it's for beginners who might not even be able to understand how can we implement this. I'm giving you a very expanded and a detailed implementation, right? Maybe you can pause here and maybe create an implementation or a phone, and that's not going to be a problem. All right, so moving on. When you come out of this while loop, there are two things. One is n is still there, and k got empty, or k is still there and n got empty. Now the problem is, if k is still there and n got empty, that means you will return -1. Why? Because that means n now has every bit 0. If n is not present, that means n is a number that's totally empty. It's 0. But k is still there. What is the meaning of k is still there? That means k still has some bits which are turned on. Let's say maybe this bit, this bit, this bit. K has still some bits which are turned on. Now, if n is totally 0, that means all bits are 0, and k is still there, that it means it has some bits turned on. Then can you ever convert n to k now? You don't have the operation power to convert a 0 bit to a 1 bit. That means you cannot convert n to k now, because if k is still there and n is not present, that's a problem. So I'll say I'll return -1 from here also, because I know after this also I don't have the power to convert n to k. But what if n is still there and k was not there? If n is still there, that means some bits in n are present. Let's say this bit, let's say maybe this bit, but k has fully turned to 0. If that is the case, what does this mean? That means whatever is the total count of leftover bits in n, I can simply take those bits and add on to my current c, because that is the number of bits which will have to be turned off in order to finally make whole of n turn equal to whole of k. So there is a very cute function for that. You have something known as built-in pop count for that. Again, just an implementation sort of a difference. Maybe you can create your own while loop for this also, but like I prefer to use built-in pop count when I have to quickly calculate the number of set bits in a leftover number. So I'll say whatever is the built-in pop count in n, add this to c again. That's all. And then I can return c at the very end. This is the whole logic. So maybe you can try to pause the video, look into this logic, maybe figure out some own logic, own code implementation, which encapsulates the logic we just discussed. And then maybe you can try to run some dry case and you will understand that, yeah, this logic kind of works. First, we'll try to maybe exhaust both bits, compare them, very straightforward. At the end, if some bits are left in n, handle like this. If some bits are left in k, handle like this. That's all. That's all we have to handle. Alright, so I hope that clears up most of our approach. Let's quickly look into the code part for this. As I explained, like that's going to be the almost same code. So intc, that's the operation count, while n greater than 0 and k greater than 0. If both bits are not same, then okay, I've done a difference, a small difference in this. Over here I compared n mod 2 equals to 0, not a problem. I just did the opposite thing. I compared is k mod 2 not equal to 0. So over here I can say that is k mod 2 not of k mod 2. That simply means k mod 2 is k mod 2 equal to 1. Now if k mod 2 is equal to if k mod 2 equal to 0, yeah. So if I know that k mod 2 is equal to 0, that means n mod 2 was equal to 1. That means I know I'm converting a 1 to 0. So I'll simply say c++, else I will say return -1. And then, okay, I missed this step over here. Then obviously you want to move on to the next two bits. So let's say you have completely exhausted these comparison of these bits, then you want them to go away. And then you want to move your focus to this position. So to do that, what you can do is, what we generally do in bit manipulation for the beginners, we try to shift by something known as right shift operator, shift this whole number to the right by 1. So what will that mean is, now let's say there are 4 green arrows I draw. What will happen is when you shift it right one time, this one green arrow will go away. Let's say this last green arrow went away. And similarly, this last green arrow will go away over here because I've shifted both n and both k. And now the last, whatever was the, let's say there were 4 bits and you remove the last bit, automatically the number is now going to be considered from here. So that is going to be the new position. And then you can again compare these last bits because they have now, the second last bits now have turned to the last bits, you can say indirectly, and then so on, so on, so on. So that's how we generally try to exhaust bits. So I'll say n left shift to n right shift to 1 and k also right shift to 1. That is simply by saying by dividing by 2 also, but that is something you must be well aware of. And then very simple condition, is n already equal to 0 and k is still remaining. If n is equal to 0 and k still remains, then return -1, and else increment c by built-in pop count of whatever is present in n and return c. So I hope this clears the problem. Now, what is going to be the time complexity? This while loop, you're basically exhausting the bits, right? Both bits simultaneously. So n and k both are given in 10^6 order. Exhausting individually one bit individual time. That means I'm basically running a log2 function, which is in like log2. You can call this as log2 of n, or you can call this as log2 of max of n comma k. Whatever is, max, not max, min of n comma k, because whichever is the smallest number, generally how many bits I have, that will get exhausted first very obviously, and that is when I'll break this loop. So that is log of min of n comma k, and then this built-in pop count runs almost in a constant time, so you don't have to worry about that. Otherwise everything is pretty constant. So overall you can say you're simply running this in log 2 of, worst case you can say, I'm running in a time complexity of log base 2 of 10^6 order, which is approximately like, I think maybe 15 to 20 iterations. I don't know, like approximately very small to that say. And basically considering us that our logic is very clean, we can definitely run this and we are going to get a right answer, not at all a wrong solution or a TLE. All right. And what about space? Obviously, I'm not using any space. I can say space is basically constant, right? That is the whole idea of the problem. All right, so I hope this clears the first problem. Let us move on to the second problem. And yeah, vowels game in a string. So apparently, according to me, I think the second problem was much more easier than the first problem. Like just to click. So like maybe the first problem also clicked very easily, but to write the first problem was kind of how bits handled and other parts. And maybe I think I did a wrong there also, wrong summation on there also. Just because of the bits part, I was not very focused on that. But I think second problem is much more easier implementation wise and clicking wise as compared to first problem. If that's true, you can definitely comment out in the chat. All right, so let's read vowels game in a string. Alice and Bob are playing a game on a string. You are given a string S. Alice and Bob will take turns playing the following game. On Alice's turn, she has to remove any non-empty substring from S that contains odd number of vowels. And Bob's turn, he has to remove any non-empty substring from S that contains even number of vowels. So you have to say first player who cannot make a move loses. We say that both Alice and Bob are playing optimally. Optimally means they're playing in such a manner that they want to win and they simultaneously also want to make the other person lose. All right. And return true if Alice wins, return false if Bob wins. So English vowels are A, E, I, O, U. That's very common. You know that. And we have English lowercase alphabets, 10 power 5 order. All right. So apparently this problem was very easy to click. Why? Let's try to look into the problem in simple approach. The string is given. Let's say S1, S2, S3, S4, S5, S6, so on. Now, let's say there is a and so on till Sn. So this is the main string S that is given to you. Now in this string, let's simply just assumably mark that, let's say S3 was a vowel, S5 was a vowel, and let's say the last letter, Sn was a vowel. So you had 3 vowels. Now tell me if Alice is with me and Alice sees that in this string there are 3 vowels. Total in this string there are 3 vowels. Then Alice's condition was she wants to remove the substring from S, which has odd number of vowels. And then she also wants that next time, preferably, Bob should not play. Now tell me, will Bob be able to play if there is nothing in the string left? Answer is no. If I don't have any letter in the string left, it's the string empty totally after Alice has done some operation, then will Bob ever be able to play? Answer will be no. So if currently Alice is standing at a string and she sees that there are 3 number of vowels in this, then will Alice think that, oh no, let me try to remove some segment or something like that? No, Alice will say, I want to win and I can also make the string empty because I know I can select the whole string. There is no condition that is refraining from me from selecting the whole string. Let me select the whole string. Whole string comparatively has 3 vowels, satisfies the condition for me, and now the string is empty. Now S has nothing. Now when Bob comes into picture, Bob will say, oh no, I don't have anything to work with, so I lose. I cannot play any turn and Alice wins. Now if this would not have been a 3, if let's say this would have been a 5, then can you say Alice wins? Yes, Alice can win. If let's say this was 7, can Alice win? Yes. If this was a 9, can Alice win? Yes. Meaning, if the count of vowels in the string is odd, then can I say Alice is going to come, remove the whole string together because the condition is this whole string is also a substring of the whole string and the whole string has odd number of vowels. I can remove this whole string into picture and now I have nothing left. So when Bob comes, Bob loses. Bob loses. This is the case for Alice winning. Now one more thing, let's try to, so this clicked very quickly. I think for all the beginners out there, this also must have clicked very quickly that why do you even want to consider some segments or something like that? Just take the whole string, you're good to go if you have a count of vowels as odd. So obviously the next condition from here very simply pops in my head. What if the count of vowels is even? What happens then? Let's say there are 2 vowels. So let's try to draw the string again. Let's say the string is something like S1, S2, S3, so on till Sn. So let's say there are only 2 vowels. Let's say S1, or no, not S1, let's say S3, and then let's say there is some middle string over here, middle character over here, let's say some S5 something, which is also a vowel. Now what Alice does? Alice is going to come, Alice starts off, and Alice says, I want to play, but I also want to play in such a manner that next time Bob does not play. So if I have 2 number of strings that is coming, 2 number vowels that are coming, or simply saying even vowels that are coming into picture, Can Alice say that, all right, if I have even number of balls that are coming into picture, and let's say there are 2, or let's say there could have been 4, 6, 8, so on. I know that I can always divide a even number like this, that I can select, if let's say from an even number I extract 1. Let's say extract 1. Then that even number will become odd because even minus 1 will be odd. And when I reach a odd number of balls and Bob is in picture to play the game, then I know Bob will never play. Because Bob cannot play if he has odd number of vowels left. So what can I do? What can I do to make Bob never play? Let's say there are currently n vowels in the string. Let's say in this case there were 2. Let's say there would have been 4, something like this, 4. Then can Alice say simply that let me take the n minus 1 vowels in a string, whatever string that becomes to be, and then crop it off. So in this case, if there are 4 vowels, let's say, so I'll say, let me pick up a segment which has 3 vowels. So if there are n equals to 4, let me pick up, let's say, this segment. And now I know this segment is totally gone. Now the leftover segment has only 1 vowel, and a 1 vowel is definitely an odd, and this 1 vowel cannot be extracted anymore by Bob, because Bob has to have even number of vowels to play. So either there are 2 vowels, 4 vowels, 6 vowels, even 0 vowels. But if there is 1 vowel left, he cannot play. He cannot do anything. So now, if Bob wants to play, what will he have to do? He will say that, okay, Alice took all the segment that had n minus number of vowels, and there is only 1 vowel left. So if I want to play with even number of vowels, I cannot, because there are not 2, 4, 6 or so on vowels. There is only 1 vowel. So my only option is to play some string which has 0 number of vowels, because 0 is also even. Yes. So Bob will come and say, and Bob will say, yes, maybe I can play, but I cannot play to remove any vowel. I can only play in that segment which has no number of vowels. So that segment will only be 1 segment left. So let's say that is this segment, S1, S2. You can very clearly see there is no vowel coming in this segment, totally removed. So Bob also turn is done. So Alice in first turn says, let me remove all the n minus vowels. So she removes that segment. Then Bob comes, he removes that segment which has 0 number of vowels. Bob's turn done. And now you have Alice. Now when you come to Alice, are you not sure that there would be only 1 letter left in that string, and that would be a vowel? Yes. Why? Because initially we removed n minus 1 vowels, and then Bob removed that segment which has 0 number of vowels. So the segment that's left now, I'll mark this in green, will be that segment which is having 1 vowel left, and that segment can be again picked up by Alice, because Alice can play odd number of vowels. So now she takes up that 1 vowel segment and totally removes, and now the string is empty. And when the string is empty, same condition. Bob comes into picture. Bob says, oh no, cannot play with anything. I don't have anything to start with. So what we have observed till now, if initially n is 3, 5, 7, 9, so on, or simply saying n is odd, then Alice wins. What about n being 2, 4, 6, 8 or any other even number? Then also I say Alice wins. But there is one case we missed. Bob can win. When can Bob win? If let's say initially in the string there was no vowel, then what happens? If let's say in this string only, the above string, let's say, the whole string had no vowels, then can Alice play in the first turn? Alice wants to remove a substring that has at least 1 vowel. 1, 3, 5, 7, so on. If there is no vowel in the string to start off with, will Alice be able to make a move? No. So only and only a condition where I say count of vowels is 0, Bob wins. So now all this bifurcation, all this theory divides into basically 2 cases. Count of vowels. Is count of vowels 0, or is it greater than 0? If it's greater than 0, I'll say Alice wins. Because if it's 1, 2, 3, 4, 5, it doesn't matter. If it's 1, 3, 5 pairs, then Alice wins. It's odd. If it's 2, 4, 6, 7, 8, 2, 4, 6, 8, so on type, we also saw, then also Alice somehow wins. So I know that Alice is always going to win if it's greater than 0. If it's only 0, then I'll say Bob wins. So that is when I return false RF, and if that is the case, I return true RT. So again, this is a very big explanation I think I gave for like 5-10 minutes, but then this idea should click very, very quickly. At least it clicked for me very much quicker, much faster to implement and much more quickly than, I should say, first problem. I don't know about you. You can definitely comment this in the chat. All right, so let us try to look this in some problem at in the test case. So we'll see what happens. Let's say this is the lead coder problem. Count the number of walls: 1, 2, 3, 4. So there are 4 walls. So what would Alice have done is, let's say I'll zoom this out. If there are 1, 2, 3, 4 walls, so Alice can remove 3 walls together. So this is the segment that will have 3 walls. Now you will only have LE. LE has 1 wall. Bob comes into picture, he'll remove this L because this is the only segment left with no wall. And then Alice removes this final E, Alice wins, true. So the case that you had 4 walls, Alice wins, so you can see it's true. But only and only false is coming when initially only the segment had no walls. Let's say B, B, C, D. No walls at all, I know. So that means I definitely am going to say Bob is going to win. Let's very straightforward approach now that you get the logic. Simply take int count of false. Count the number of false. Is it greater than 0? Return true. Is it not greater than 0? Return false. That's all. What about the time complexity? Obviously, you're running a loop in the order of n for the string. That's order of n, and space constant since you're not using any extra space. Alright, so I think very simple and easy problem. Let us move on to the third problem. Maximum number of operations to move ones to the end. So kind of an interesting problem, right? You like some dry running and dry paper testing was required in this. All right. So you are given a binary string S, that means either 1 or 0 in the string. You can perform the following operation on the string any number of times. You choose any index I from the string where I plus 1, it's very important, this thing is important. You choose any index from I where S of I is 1, I plus 1 is obviously less than S dot length, S of I is 1 and S of I plus 1 is 0. So you are having a 1 and a 0. If you look from the left hand side, if you look from the right hand side, you have a 0 and a 1. And then you move this character Si to the right until it reaches the end of the string or another 1. For example, let's say this is the string given 0, 1, 0, 0, 1, 0. Then you pick this one, and you can, if you pick this one, why will you pick this one? Because this one and the next letter is 0. So you can pick this one definitely, and then try to keep it moving to the kind of rolling it to the right hand side, and you roll it till you reach another one or the end. So over here there is a 1 kept, so that means this one will roll to this position, that's all. So if that's what written, if we choose I equals to 1, resulting string will become 0, 0, 0, 1, 1, 0. So I have this rolling function, like rolling a feature of 1 to the right hand side makes sense. All right. And the main question is, how many maximum such operations can you perform? So this thing we did, we picked a 1, we rolled it to the right hand side till I stopped. Either it was end or another had a wall of 1 there, you can say wall of brick of 1 something. Till what did this was an operation. Now this operation is counted as one operation. How many such operations can you perform? And if you can perform many such operations, tell me maximum number of operations you can perform. That's the logic. Right, so maximum number of operations we need to perform to move ones to the end. That's the whole idea behind this. All right. Now, why have they written move ones to the end is because obviously if you want to maximize your operations, let's try to look into a picture over here. Let's say this was the string initially. What they did was, after they said there are 4 operations, forget how this 4 is coming, or let's say this 4 is assumably the max. But look at the final string. If I take whatever I want to do at the very end, I know that I'm going to receive a string that looks something like this. That means all the ones that were present in the string, in this case 4 ones, everything is going to roll towards the right hand side, because that's how I would receive the maximum number of operations. If I don't do that, if I stop somewhere and I say no, all the ones have not shifted to the right hand side of the very end of the string, then I know I have some more operations to do. If I have some more operations to do, I'll say definitely a problem for me. I don't want to stop over here. I want to achieve more number of operations. So the ideal thing over here is to understand that eventually I'm trying to create a string where all the ones have rolled towards the right hand side. If this is 1 0 0 1 1 0 1, then this one should eventually roll to the right hand side to look something like this. All right, so I hope this should be very clear. And if they were already rolled all to the right hand side, then the answer is obviously 0. So now let's try to analyze this case, whatever they have given as choosing this index and so on. All right. So let's say, assume you had something that looks like 1 0 0 1 0 0 1 0 1, something like this. Now, when I saw this question, my main idea was to understand how will I receive the minimum number of operations. Now, why did I do this is, what happens in problems is, let's say you're able to figure out what is going to cause you to go as low as you can in some operation or in some technique or something, then it kind of paves a path to think, if this is how I would receive the minimum, then just doing the exact opposite might give me the maximum. That's the idea behind the problem. So again, this is my intuition, my logic. Maybe you can come up with some other logic. So when I saw this problem, my initial thought was, when I am receiving the minimum number of operations. So this minimum operation thing was very, very easy to think. I know that if eventually I want this string to look something like this, that's 0, 0, 0, 0, 0, 0, then you have 1, 1, 1, 1. This is what I want to look at like. Now, if I want it to make it something like this, that means what I can do is I can start picking each one. Now, where would I pick a 1 from? If I pick a 1 from here and then move it, or if I pick a 1 from here and then I move it. Let's try to think this in a very simple case. Currently, you have, this is the positions that you currently want to achieve. That is, last 4 should be 1. And over here, you have this number of positions. So from the right hand side, this 1 bit is already present. That means this 1 is there, no need to hamper it. Let's go to this bit. This bit is 0, or sorry, not bit, I'm sorry. This character is 0 and you want it to be a 1. So ideally you want to make it a 1. How would you do that? If you turn your head to the left hand side, you will just find whatever next one comes. And whatever this next one comes, can I say that this is going to act as a wall and this one can roll to this position? I'll say yes, that can happen. So how will that happen? Simply pick up this one. And now I have something that looks like 0, 0, 0, 1. And now I'll say these 2 bits are now set. These two, sorry, not bits again, my bad. These 2 characters are now same. So I know I'm good to go. Now I'll move my focus to this next 0. Oh no, a problem. Want to make it a 1 because this should match, but I don't have. So I'll turn my focus again on the best left one that is present, act this as a wall and shift this one over here. So now I have something that looks like, I will have something like, this is now 1 and this is now a 0. Good to go. And then same logic, bring this. This is a 1 and this is a 0. So how many number of operations did I take? I took 3 operations. And my argument is I cannot go below 3 because that is how I would be shifting somehow all the characters or roll all the ones to the left hand side. But look at the technique what I did. I'll go back again. So remember I had 3 number of operations when I was doing this technique. The technique was 3 number of operations when I was looking from the right hand side, trying to roll 1 1 number like this. That was the best case. Just the opposite. What if I start from the left hand side? Let's see now. If I start from the left hand side, what will happen is this one will try to roll. When this one rolls, this one is going to roll and it comes over here. Now you have 2 collective ones. Now when you say that I don't have any 0, I don't have any ones left to the left hand side, my focus will be now, like again, I'm trying to maximize my number of operations. So I'll say, all right, I only want to do the vice versa thing. So let me just now focus again from the left hand side only. From the left hand side, what ones can I move? I'll say this one can be moved. Just next now, this one can be moved. I cannot move this one because this one to move, there is already a wall, cannot move this one. So this one can be moved. Till which position? This position. So I'll say, all right, move this one. And then I have placed over here. And then this is 0. Then I'll say, all right, now which one can I move? I can move this one. Take this one. This becomes a 0. And now I have something that looks like this. 1 1 1 0. So now I can say that I'm going to move these 3 ones one at a time. So same logic, bring it over here. And this would have been a 0. Bring this one over here. This would have been a 0. Bring this one over here and this is a 0. And finally you receive 1 1 1 1. Now tell me, what is the number of operations that you now utilized? Did you utilize, like you had 1 over here, so 1 plus 2 plus 3. You utilized 6 operations. And can we see that this is the largest? Why? Because technically what we're trying to do is, we are trying to say that, like I'll go back in the string again. We are trying to say, look into this observation very carefully, that initially whichever is the one that is second in number from the left hand side. This is the second one. Make it a wall and collect everything till here. So I'll say if this is a wall and everything before this should be collected, then I'll say before this, how many number of ones are there? One number of one is there. So I'll say this one number of one should be collected and placed at this location. So this one shifts and comes at this location. Good to go? Yes. Now what happens? Now I'll say, all right. Now the next wall would be this one. So if this is a wall, everything before this should be rolled. Now everything before this, if it wants to roll, then obviously how many number of ones are there before this to roll? There is this one and this one. So if I want to make this one roll, then I'll say this one rolls and this one rolls. Good to go. And I'll say, yeah, I have +2 number of operations added. And now these two ones again roll. And now I have something that looks like this. And now the final operation, you will say, all right, go to the last one, make it a wall, and whatever comes before this, try to roll it. So I'll say, all right, roll it. Fine. Cool. Make this one, roll over here. Make this one, roll over here. Make this one, roll over here. Number of operations added? 3. And I'm good to go. So what eventually did I do? What did we see that we are trying to do? We saw that if you are standing from the left hand side and you keep on making every one except the first one a wall and try to collect everything before that, that's all the ones coming before that, 2 at that position, you will increment your number of operations drastically. Now, why am I saying this is because this logic is coming from a very simple, like a sort of a greedy manner, you can say. Greedy would be a good term to do this. Greedy logic that every time I am not creating the wall in a very right hand manner, I am creating a wall just at that position. And I'm saying from the left hand side, create this as a wall. Move on to the next wall, move on to the next wall, move on to the next wall. So I'm trying to collect ones every number of time, which is drastically going to increase my number of ones. All right. So this is the whole idea behind the problem. When we say that we can try to create, except the first one, the second and so on ones as walls at a single point of time and try to collect ones, so on, so on. So let's try to implement our idea, and we'll see one corner case also in the test case over here. All right. So let's say this test case was actually this. That's 1 0 0 1 1 0 1. So what I'll say is from the left hand side, first find the second one. I cannot talk about the first one. First one cannot act as a wall because before that no one is coming. So this one becomes as a wall. Okay, wall made. Everything before this collected. So everything before this is only one is coming. Collect it. This becomes one operation. And that would look something like taking this one and moving this one at this location. So good to go. I'll say, all right, I am good to go. And now the string somewhat looks like this. That is 0. This is a 1, 0, 0 and 1 plus operation. Now look very, very forward. You were considering this one to be a wall. And now you will, obviously, I said, shift your focus, on this one. That's the next one. So I'll say, all right, this becomes a wall. But tell me, before this wall, do you have a 0? Answer is no, I don't have a 0. Why? Like just how I shifted it. I don't have a 0. Now the problem is, if you don't have a 0 over here, remember, like this is a mistake that I did. That's why I don't want you to repeat it again. You forgot, or you must have forgotten this sentence. To roll some current one to the right hand side, the next upcoming just character should be 0. So if I say that I would be trying to roll this one, is it possible? Everything that's coming before that, can I roll it? It doesn't make sense. I cannot roll it, right? Very obvious. And that's very clear also. Even if I want to roll it, I cannot because it's already rolled. I have already one already kept to the very end of the wall. So I know I cannot roll any further. So the check in the code where I would write would also be that if I'm standing at a current one and I want to make it a wall, then the previous should be a 0. If it's not a 0, then how will the other ones come to that? If it's not a 0, that means already everything has been shifted. Everything has been shifted to the right hand side of the wall. So that's another test case now. Now I'll say, all right, this one failed, made it a wall, checked how can I increment, but saw nothing to be incremented. So move on to the next one, make it a wall now. And now I have a 0. That means something can be shifted. And I'll count how many ones are there. There are 3 ones before this. That means I can shift this one, shift this one, shift this one. And that would create 3 rollings for me. That would make a total rolling of 4. Or let's again, this is very, as I said in the very start of the problem, this is a very observation based problem. You have to sit with a pen and paper and make cases to understand that, yeah, this is the highest I can go. And if I want to go highest, this is the best approach I can follow. I have also like sat down for like 5-10 minutes, made some cases, and then I was able to approach to this. So if you're not able to do this, sit down. It's kind of an ad hoc greedy problem. So try to understand how you can make some cases, good cases, try to understand what will happen, and then you will automatically prove yourself that, yeah, this is the optimal I can go. Now let's talk about implementation. How can I do this if I want to implement this? So as I was trying to implement the sentences as I go, you can very well see what I did was every time I had some string, like I'll make the whole string. Yeah, this was the initial string. Every time I was standing at a 1, I was first seeing whether the previous number is 0 or not. Sorry, previous character is 0 or not. And if it is, then all the ones that follow before that wall, I will count that. So can I create a prefix array of ones if I want to calculate this very quickly? A prefix array of 1 would simply denote that if I create array like this, what is the physical meaning of this? It would say that prefix ones of I is equal to number of ones till ith index. That's the whole definition in the initial string. So can I say, like, I don't want to virtually move the roll. I don't want to make all the letters move because I know that's not going to be ideal. But imagine this, that even if you don't roll them, eventually just counting whatever is the number of ones that follow to the left hand side of a current wall, those are the number of times you must be utilizing your operation. And that's true. Let's look over here. If I would have created a prefix array out of this, it would look something like this. 1, 1, 1, 2, 3, 3, 4. Yes, over up, because till this index 1, 1. Till this index only 1, 1. Then till this index, now I have 2 ones. I have 2 ones, 1 and 1. Till this index, 3 ones. Till the last index, I have 4 ones. So this is the prefix ones array. Now, when you're standing at this wall, before this, how many ones are coming? If let's say the previous character is 0, yes. So before this wall, how many ones are coming? You can simply check this by saying whatever is prefix of I minus 1. You will say, yeah, prefix of I minus 1 is 1. So I'll say operation gets increased by 1. Because those are the number of ones I'll be trying to roll. Now move on to the next wall. Cannot do anything because the previous number is 1. That means a problem for me, cannot roll anything before this wall. So don't make a wall over here. Move on. Next place over here. Make a wall. Before this, how many ones are coming? How do I calculate this? Prefix of I minus 1. So if I'm standing at this as I, prefix of I minus 1 is 3. So I add operation plus equal to 3, which indirectly would have meant that these are the 3 ones which would have wanted to roll to the very end of this wall, this green wall I just drew. And that gives you a total of 4 operations. Alright, so this is the whole idea behind how you would implement the problem. Alright, so I hope this should become clear. Let us look at the code part of this to understand it much more clearly. Alright, very simple now. Take the n size, take a prefix 1's vector, create that vector. So s of 0 is 1, prefix of 1 is 0 is plus plus. Start from 1. Prefix of I would be prefix of 1s of I minus 1 plus is the current letter I 1 or not. If it's, then add 1, else add 0. Make an answer variable. Start off with 1. Right, the index 1, because I know I don't want to start from the 0th index. It won't matter a lot. Is s of I 1 and is s of I minus 1 0? If that's the case, increment prefixes of I minus 1 into your answer. And then at the very end, a small check, is the last letter 0? If the last letter is 0, that means what would have happened is, initially the string would have looked something like this. 1 0 0 1 1 0 0 1. So now everything that comes is still this picture. But this, you know that eventually you want all the ones to shift to the very end. If you want them to shift to the very end, that means there is something that's already left there. So also taking that case into consideration, you will have to place a final check, corner case, s of n minus 1. Is it 0? If it's 0, that means still some rolling has to be done. And n size should be greater than 0, greater than equal to 2. Why? Because I want prefixes of n minus 2. So n minus 2 index should exist, right? That's why n should be greater than equal to 2. What will I add? If this becomes a wall, that's the final place, that's the very, very end of the thing becomes wall, then whatever is the number of, like you can say whatever is the count of ones that are coming before this wall. So that is what I have just simply added on. So I think very ad hoc based problem, I should say. You can sit down with a pen and paper, try to understand that yeah, this would be the most optimum way to go, and then only you will be able to fully grasp the problem. All right. So what is the time complexity? Runs in order of n. This runs in order of n. So I can say very simple. Time complexity is O of n. What about space? I'm using an extra prefix array. So you can say that space is n. So space is also O of n. Now what a 10 per 5 order, I think. Yeah, 10 per 5 order. Good to go. Definitely fulfills me a good solution. I think gets me accepted. Yep, gets me an accepted solution. All right, so very basic simple problem. Let's move on to the fourth problem. All right, so this is kind of a hard problem. Like it's tagged hard, obviously, but otherwise also the logic otherwise might be very hard to generally picture and do. So like I'll go in here and accept that there is a sort of a question I've done similar to this previously. So I kind of took my idea and approach from there. But the whole idea, I'll try to bring it down to very short and good points so that you're able to catch up with the whole problem. All right, so just let's see how can we do that. Minimum operations to make array equal to target. So you will be given two positive integer arrays, nums and target. Both are going to be of the same length. So let's say length is n. In a single operation, you can select any sub-array of nums. So sub-array means that you're selecting some continuous segment of nums and you're selecting that and incrementing or decrementing each element within that sub-array by 1. So either you choose you want to increment or decrement. And if you choose, let's say I want to increment, I will increment every number in that sub-array by 1. That's the logic. And then return the minimum number of operations required to make nums equal to target. All right. So let's look at this test case. Let's say you have 3, 5, 1, 2 and the target was 4, 6, 2, 4. So initially what you can do is you can increment the whole array by 1. So I'll say I'll increment the whole array. It's kind of saying that I took the sub array to be the whole array. Increment every number by 1. So this becomes 4, 6, 2, 3. You can say 4, 6, 2, 3. And then you can increment the last number by 1 again. That's a different operation. That becomes 4. So eventually you get 4, 6, 2, 4, which is actually the target array. Good to go. And you have minimum 2 operations. And like I should say, the approach is to, the claim is to say that 2 is the minimum number of operations I can go. Similarly, over here, let's say I have 1, 2, 1, 3, 2, and I want 2, 1, 4. Then I can maybe take this array. That's a singular subarray of single number, incremented by 1. It becomes 2. Take this subarray, decremented twice, so it becomes 1. And then take this array, incremented twice, so this becomes 4. And eventually you have 5 operations. All right. So that is the whole idea, like how the test cases are working. Obviously, you can draw some more test cases to figure out or your own, minimum operations you get. But let's try to first look at the problem in a much simpler sense. So what I'll do is we'll try to jot the problem in its constraints. Try to start off with some fewer constraints, some fewer iterations of the problem, and then try to figure out the main problem. All right. So number one iteration that I'm going to do is over here. You can see that what nums of I and target of I both are in 10 power 8 order. That's given. But over here currently what you want to do is you want to make this current array go from nums to target. I can modify this question and say, let's say I'll take this example only. The target array was 4, 6, 2, 4. And the initial nums array was 3, 5, 1, 2. Now let's say I subtract, I try to find out what is the difference that I have to cover in a new array. Let's call this D. So this is the target array. This was the nums array. And I said, if you subtract 4 minus 3, you get 1. 6 minus 5, you get 1. 2 minus 1, you get 1. And 4 minus 2, you get 2. So can I say that this is the array of the difference which I want to make covered in the nums array so that I receive a target array? Yes, I can say that. Or in a better way, can I say this now that assuming that this difference array was something you need to cover, can I assume that initially the nums array was 0, 0, 0, 0 and the target array was not 4, 6, 2, 4, actually 1, 1, 1, 2. I can say this now. Why? Because what I've done is I've done a very small modification where I have kind of said that every number in my nums is acting as an origin now. It's kind of a point where every number has become in nums 0. And then what my target array would be, what difference do I have to cover? Because that's what I'm trying to do. Like if let's say you're able to, I'll ask this question to you. If let's say I answer the question for this modification, let's say I tell you that initially the nums array was 0, 0, 0, 0 and the target array was 1, 1, 1, 2. Then let's say the number of operations to convert this, let's say just the minimum number of operations, somehow you're able to do that. The best minimum number of operations to convert this was OP. Then can I not say that this OP is the same amount of operations you would have required to convert a nums array that actually was not 0, 0, 0, it was 3, 5, 1, 2, and your target array would have been 4, 6, 2, 4. Same thing, because I know that all I have done is if I have deduced or subtracted a difference from every of the number in nums and target as well, just because I want to make my problem much more easier to visualize. That's why I've done this. Now I'll tell you why I have done this and what do I mean by when I say I wanted to better visualize. All right. So I think this point must be very clear that the number of operations to convert an array that's initially 0 to an array that looks like 1, 1, 1, 2 is equal to the number of operations required to convert an array that initially looked like 3, 5, 1, 2 to an array that looked like 4, 6, 2, 4. It's very obvious it's going to be the same number of operations because the difference between both of them are same. Over here difference is 1, 1, difference is 1, difference is 2. And over here also the difference is same. This is difference 1, obviously this is difference 1 and this is difference 1 and this is difference 2. So you're trying to basically cover the same difference array, that's 1, 1, 1, 2. If you're trying to cover the same difference array, then whatever number of operations you will require, it will be the same for this case also and same for this case also. So I think this is our very, very number one point of justification, point of observation in the problem. Now, why I have done this? Let's see. Once I do this, now what the problem is, the new problem has converted to this problem. This was the initial question, but now you have modified the question to a new question where the question has now become initially given an array of all zeros. Create target by either incrementing or decrementing any of the subarray by one. This is the new problem. Now let us try to focus on next bifurcation. So first modification that I did was this. Again, this modification was not kind of a modification where you say that the answer changes. I know that whatever answer I would have calculated from here is the same from here. So it doesn't matter where I do this. It's just that you will ask, why did you do this? Why did you modify your question to look like this? Because now what I can do is, I can now modify my question into two different cases. I will say one case that, tell me, over here we can see, if I start out from nums and I'm talking about this target array, just for example, I'll take more cases to example that out. Over here, this target array is all positive. It's all positive. You want to create a difference of, you want to jump 1, you want to jump 1, you want to jump 1, you want to jump 2. So tell me, although you have been given the power to also decrement any subarray by 1, in this case, will you want to decrement? For just this case, I'm not talking about other cases. I'll take more cases to explain. But right now for this example, we are only concerned with the incrementing because I know in this case, only increment will give me the correct answer. I don't want to decrement. It doesn't make sense. I'm at 0. Why will I go to some -1, -2 value and then come back to 1? Doesn't make sense. I will try to obviously go to 1 directly or 2 directly by incrementing. So for this case, which we just discussed, test case number 1, we only are concerned with incrementation. I'll obviously take decrementation. So just wait and watch for that thing. So I have boiled down my question to saying that, let's say initially the array was all zeros and the target you wanted to create was only by incrementation, because in this case you wanted to increment all the value because initially you are at 0 and the target value, every value is greater than equal to 0. So if every value in target is positive, then you want to always increment. So that's the new problem now. Now let's look into this problem in a very different sense. Let's say the test case, I'll modify the test case a bit. Let's say the target array looked something like 3, 1, 5, 3, 2, 4. Okay. Now I'll draw some number of blocks. All right. So let's say this is block. This is the first place. Okay. Let me draw it a bit neat. All right. This is block. It had 3 total value. I'm just modifying the array to look in a block format. Then this is the second index. This is 1 block. Then this is total of 5 blocks. 5 blocks over here. 1, 2, 3, 4 and 5. Now I have 3 blocks again. So this is 3 blocks. And then I have 2 blocks. And then I have 4 blocks again. Sorry, I made 5 blocks actually. This can be 4 blocks total. Okay, cool. Now let's say, we can very clearly see that this was the ground 0. This was a value 1. This was a value 2. This was a value, you can say like something like this. This is value 1. This is value 2. This is value 3. This is value 4. And this is value 5. Now tell me, initially your array is 0, 0, 0, 0, 0, 0. From here, you want to jump to this position. Now tell me, can you imagine something like this? There was a game known as Tetris. Try to imagine it kind of like this. What happened in Tetris was, when you made a full row, then that row used to vanish. That's what the game of Tetris is about. I mean, I'm not trying to say that if you don't know Tetris, this problem is not solved. I'm just giving an example. What I'm trying to take is, I'm trying to take the same example and say over here that given that you have the power to select one subarray at a time and only increment it by 1, ideally, can you imagine this, that initially you are standing at this position. That's everything is 0. Now, move your hand with me. Tell me, if I say I want to take this bar to 1 above, can I say I'll take this bar 1 above? And to take this bar 1 above, I have a single block which is ready with me, which means that every number right now, that is all these 6 numbers, 0, 1, 2, 3, 4, 5. All these 6 numbers or all the numbers on all the indexes require 1 addition. So can I say that I can increment right now my whole subarray by 1? If I do that, what happens now? My initial array looks something like this. Now. It becomes 1, 1, 1, 1, 1, 1. And operation count has become 1. And what has happened is, imagine in this block format, now you can say that this blue block of line has been covered. Because now, every block has been covered in in this one block over here, making your current array look like 1, 1, 1, 1, 1, because you have automatically incremented every number by 1 from 0 to 1, and now you have this left. Now tell me, can you observe over here that this part has matched? This one, you wanted a 1 over here and you got a 1 over here. So you can say that index number 1 has fulfilled its condition. Yes, index number 1 has fulfilled its condition of creating the same number. And I can see also over here, can you see this block? I'll mark this with black. There is a block that is not present over here. There's a small bifurcation over here. So what does that clearly mean to me? Now, if I jump to level number 2, level 1 was done. If I jump to level number 2, can I see that there is one block over here and then there is a range of 4 blocks over here which need an increment. So if I ask you, how many number of operations will you require more to jump or finally cover your level 2 also? Will you not say that I will require 2 operations? One operation to cover this one block, and one operation to cover all these 4 blocks. So I will say that initially what will happen is my next operation will be that take this segment. I'll show you which segment. Take this segment and increment that subarray you can call this, incremented by 1. So this becomes 2, this becomes 2, 2, 2 and 2. And you can say now you have covered your block level 2 and your operations have now become 3, because that is this subarray you selected, this subarray, and you would have selected this single subarray of single number. And now your level 2 is complete. And let's talk about the further level. Okay, I forgot to draw this. Yeah, this is block. Now let's talk about the level 3. In level 3, can you see that I want 3 bifurcations? I will have this bifurcation, I will have this bifurcation, and I will have this bifurcation. I will say yes. So that would mean now I would require, because I can see very well that this 2 is matched with this 2. That means there has been a gap that has been created, which is very clearly visible over here. We can see this gap. This gap is no longer with me, which tells me that this number wanted to increment till 2 places and it has been done. You covered 2 levels, good to go. But now move forward. And that gap has been created. So that is now giving you a gap in between, which is telling you that this is where you have to stop. Now the segments have increased, and now the number of segments you will increase is these 3 segments. There would be this segment, this becomes like this segment, it becomes from 2 to 3, incrementation. This segment, this becomes 2 to 3, 2 to 3. And then this last segment, this becomes 2 to 3. And you are done with level 3 also. And you can say my number of operations have incremented to 6. All right. And then let's talk about level 4. Level 4, you will require 2 operations, one over here, one over here. So that would mean 2 segments you will increment. So that would mean this segment. That means now this value becomes actually 4. All right. This value actually becomes, you can say 4. And the last segment also, that value also becomes 4. And this segment is also covered. And now your number of operations have turned out to be 8. And then the final segment is covered. And this level, for this level, one only segment is covered. And this becomes 5. And you are good to go. Now your array looks like 3, 1, 5, 3, 2, 4 as expected in the target, starting from 0, 0, 0, 0, 0. And the number of operations you required to do this was actually 9. And I think like I have tried to keep it very visualistic just because of the reason. So I think up till here, if you are not clear on this part, you can pause the problem, look in this like 5 minutes of loop again to understand this visualization, maybe draw some case of your own and maybe try to use the same case over here on this array I draw, creating a difference from 0, 0, 0 to 1. I mean, this was a very easy difference. That's why I took a different test case. But if you want, you can try that on that also. This block method should be very clear. This block method is so clear that it's helping me figure that yes, this is the number of operations I would have actually required to get myself the best case in which in minimum number of operations, I can go from an initial 0, 0, 0, 0 array to a new array. And now this algorithm is not very new. This is something that might for like not beginners who are not out, like people who must be into Leetcode problem solving or not, you must have done some problem like this where initially you can be said array was 0, want to convert it to a target array with only incrementation. Alright, so this solves our case. Now this is where, now I have bifurcated my problem into a further piece. Now I said initially that your initial array was 0, 0, 0 and you wanted to go to a new array. But in this array, every number was greater than equal to zeros. That is why you only wanted incrementation. But the problem is, if you look at case number 2, the initial array is 1, 3, 2. And then you have a target array that's 2, 1, 4. Let's calculate the difference array. Difference array is 1, -2 and 2. That means if I tell you that initially your array was 0, 0, 0 and this is your actually target array, that's the new target array. You can say that I don't have the power to say every number is greater than equal to 0. Is every number greater than equal to 0? This is positive, but this is negative. That means my logic right now, which I told you, only works when I said that this block formation can be done for when you want it to increment. So this incrementation makes sense, but you don't have always incrementation. You also have decrementation. That means over here you can see I wanted to go lower than 0, then I will have to decrement this. What do I do now? And extending to this, what can happen is, let's say your nums initially, if it's 0, 0, 0, 0, 0, let's say 6 numbers, let's say, your target doesn't always have to be all positive. It can look something like maybe -1, -2, 3, 4, 5, -6, something like this. Then what happens? Then what do you do? Very, very simple. This is where it's going to be a wow moment. We just calculated our algorithm when we wanted to convert whole array from 0 to a new array that was all positive. Now tell me, this is by far the best idea to calculate the minimum number of operations for an array which wanted to convert itself to a fully positive array. Now let's say over here I have some negative, some positive. Can I bifurcate this array into sub-arrays of positives and negatives? Can I say this is one segment that's all negative, this is another segment that's all positive, and this is one segment that's all negative? If I do this, now can I say this is 3 separate problems for me to solve? Why? Because I can say that over here, let's see if this was individually one problem where I would have said your initial nums array is 0, 0, 0. You want to convert it to 3, 4, and 5. Then could you not have said that if I have a function which tells me this number of operations by this logic which we just implemented, I can just call that function for this part of the array and I will get the number of operations. Yes. And then what about this segment and this segment? The only problem in this segment is every number is negative. But how is that a matter for you? Can you imagine it like this? We saw that we were at level 0. This is the level 0. Below this level, there is level -1, level -2, level -3. Imagine that this was a mirror. Imagine that this was a mirror. Then what would have happened? Can I say that this block would have mirrored in this I should say like in this mirror, and you would have created a block like this, like a diagram like this, something like this. Yes. And then can I say that that would meant you're trying to create negative difference now. That means you're decrementing, because over here your option would be to only decrement. Over here you will be decrementing, over here only incrementing, over here only decrementing. So eventually what is the case? For an array that's fully negative, will the same algorithm not work? It will work. I will just need to make a small modification that in this array, I can first convert all the numbers to positive. Because I know that it doesn't matter for me whether I'm calculating the answer for a mirror value in the blocks above or the same blocks mirrored down in the negative levels. Answer of operation will be same. Because if you think like this by logic, whatever answer you calculate for the block creation of levels in the top 1, 2, 3, 4, 5, same would have been done if your negative levels would have been reached. -1, -2, -3, -4. This would have been -4. And this would have been -5 below that. That is the same amount of effort you would have done and same amount of operation you would have required. Because of that, I can say that it's kind of saying that it doesn't matter for me as long as the whole array is negative. I can convert all the numbers to positive, like not convert in the array, but maybe create a copy, and in that I can do that. And then I can run the same algorithm. Let's call this algorithm a box function. Run this box function over here, run this box function over here, run this box function over here, and then calculate your answer. So if I run this box function over here, whatever answer I get, let's say OP1, add that. Whatever box function I get over here, let's say OP2, add that in a number of operations. And whatever I get for this, let's say OP3, I get it over here. And then I can add everything, and that gives you my total number of operations. And this fully satisfies the problem. Now I have also used incrementation and decrementation in some segments of the array to create a difference that was required. Initially the difference was, let's say, assuming the difference was, I said somewhere the difference was -1, -2, somewhere was 3, 4, 5, somewhere was -6. So let's try to revise the problem again. First, I said that although the array looks like this, because I know that I can create a new array which initially starts with 0 and try to cover the same difference, number of operations required or the answer that should come for this case will be the same number of answer that is going to come for this case. That is point number 1. Once that is understood, I now bifurcated my problem into 2 segments. First, I said, let's assume that all numbers you want to increment to are positive. If you want to do that, we can follow this approach, a level-wise block visualization approach, where I can very well clear out my answers. I can figure out my answer. Now I'll obviously come to the part how by implementing this thing. I have not discussed this now. Just wait a second. All right, I'll discuss this. And now I'll say that, all right, assume that you calculated this in a good time complexity. Now I bifurcated my next case and said, finally, when we did this for a positive looking difference array where the target was all positive, initially I know that my target array can also have negative parts, some negative, some positive, some negative. So what if I bifurcate my target array into segments of negatives and positives, and then I can tackle each segment separately by this function checker box that I would have created with this mirror based approach, knowing the fact that this same function can be run for all the segments, since negative sign doesn't affect me to calculate the answer. Negative only means that everything has been mirrored, or this block can we say it has been mirrored in the down segment to create the same logic. All right, so you can very well visualize this, like for answer of -1 and -2, whatever answer this should come from, this will come the same answer from 1 and 2, because eventually the absolute difference from 0 is same. That's why I've called this mirror approach and everything. Again, very detailed terms I'm trying to picture. If you want some simpler terms, I think up till here only, just by listening to this logic, you will get the problem. So you don't need to listen after that. But for beginners out there, this absolute difference being the same is why reason I'm saying that negatives and positives sub arrays can be handled separately and can be handled with the same function, because I know that it doesn't matter to me how I'm calculating the number of operations. Am I going down or up? It simply matters to me is I'm quickly calculating them in this block visualization approach. All right, now comes the main point. All the storyline has been done. Now we'll see this final segment. I calculated these blocks and I was marking these blocks, but I cannot do them actually in the code, right? There has to be some other logic of code. How can I do this? So let's imagine this. Look at these blocks and I'll draw some line over here. Look at this line, this green line. Then look at this line over here. Then look at this line. Add the length of these lines. You can see this line is of 3 length, this line is of 4 length, and this line is of basically 2 length. If I add them, 4 plus 2 plus 3, that gives me 9. And remember, for this array, we had calculated that there would be actually 9 number of operations required. So what did I do actually over here? Let's try to see. What I said was, eventually what do you want? When you clearly visualize this block method, what you want is eventually what sort of a spacing is there when you actually are covering, like there was a gap over here. And this gap could have been covered by the next segment of 4 height total. Like we don't want to go till this height, only this 4 height, which would have meant that I am covering this part, this part, this part, and this part. When I said I'm covering this, what does this mean? I'm covering this part and this part. And when I say I'm covering this, what does this mean? I'm covering this part, and this part. So can I say that when I'm standing at a particular index, whatever comes before that, if I calculate the difference and I add that, if that difference is positive, will I not get that number of operations for the segments it might be covering? Yes, I can start off by saying that my answer currently is 3. That's the height of this block. Then the height of this block is 1. This is 4. This is, this is 5, This is 5. This is 3. This is 2. And this is 4. So the array is 3, 5, 1, 5, 3, 2, 4. I will say initially my answer starts off with 3 and I stand at this index. Now 1 minus 3 is negative 2. I know negative 2 doesn't make sense because I know negative 2 blocks I'm not covering. So I'll say plus no operation, 0. Come to this index, 5 minus 1, that's 4. Add it because I know that means 4 blocks would have been kept over here, which would have covered these 4 segments for me to later cover as a sub segment in my operation. So I'll say 4 operations get added. Then come to this index, 3 minus 5, negative 2, not possible, only 0. 2 minus 3, not possible, 0. 4 minus 2, yeah, a difference is positive, 2. 3 plus 4 plus 2 eventually gives me 9. And this means I have covered all these segments. So this is the idea behind the problem. So what I'll write is a very small piece of code. Now I'll not go into more detail of how dry run this code over here. I'll show you the code. All right, let's try to catch up with that part. First, we look at the test case number 2, which we were trying to discuss. All right. So I think, yeah, test case number 2, 1, 3, 2, and you wanted a target to be 2, 1, 4. So the difference will become 1, negative 2, and 2. That means you would have started from 0, 0, 0. Bifurcate this to positives and negatives. Positive array, negative array, positive array. Okay, I'll do the change pen. Positive, negative, positive. Now I'll convert this 0 to 1. That would take a total of 1 degree. Negative 2 to 0. This takes a total of negative 2, so 2 degree. And this takes a total of 0 to 2 takes a 2 degrees, so this becomes 5. Now this is a very, very simple test case. So over here, it was very visible that how much operations do you want, but maybe you can calculate for this, right? Maybe you can calculate for this, that over here, you will see that the number of operations are going to come as low as possible. Like calculate your answer for negative 2 and negative 1 and negative 2 by simply making them first all positive by running through this checker function. You will get some answer. Answer will definitely be, I think, 2. That is first, okay, let's try to actually imagine this also so that there's no confusion. Final case I'll take for you for all the beginners. So negative 1, negative 2, all right. Then this is 3, 4, 5, and negative 6. So I'll draw this on the block sense and you'll say, this is the mirror line, all right. So negative 1 means 1 block down and 2 blocks down. Then positive 3 means 3 blocks above, 4 blocks above. Okay, I'll say 3 blocks above, 4 blocks above, and I'll say 5 blocks above. And then negative 6, so this is negative 6 blocks down. This is what I've done. So 3 blocks, 4 blocks, 5 blocks, 1, 2, 3, 4, 5,
6 blocks, 1 2 blocks, and 1 block. Now I'll say handle this separately, and this separately. So calculating answer first for this segment, this tower I have created, this skyscrapers I have created. One operation over here, one operation over here, one operation over here, one operation over here, and one operation over here. That means 5 operations. Over here, one operation over here, one operation over here, 2 operations. One operation, 6 operations. Total you get 13 operations, and that's the correct answer. You will definitely get this. Like, you can actually try to run this, maybe make some more cases on your own. You will see that, yeah, this is the correct answer that I would get. All right. So I think that clears up most of my problem. I think this problem will take a lot of time than if I go into every test case individually. You can take up some pen and paper of your own. You can try some test cases on your own and try to figure this idea. All right, cool. So let's look at the code part now to understand this. Okay, very simple code now once you get the logic. Calculate size. Then what I've done is first decrement every target of I with nums of I. That's why that is the conversion I've done, so as to say that now initially my target is to start from zeros and then convert it to target of I. So this is what I've done. This conversion. This is case 1 conversion which I showed you. First point conversion. First point which I showed you over here. First point conversion. Alright. Now I have a vector of single array. I have an answer and I have vector of segments. These are the segments or the sub arrays or the segments I'm trying to bifurcate. So this is the positive, negative segments. Now I go into the array. I say, is the single array size 0? If it is, push target of I. If the back is less than 0 and target I is less than 0, push back target I. If the back is positive and the target I is also positive, push back target I. Else, if you are currently standing at the back, which is some other type of it is either negative or positive, and the target that you now received is positive or negative, then you will say that I have opposites. In that case, I will push back this single array in the segments because this would create a positive or a negative, whatever that was a segment for me. Clear this array and then I will push back target of I. So this logic I've written is just to say, if I would have given you a different question of a easy or medium Leetcode question, bifurcate your main array into sub-segments of positives and negatives. How would you have done it? You can do it as you want. Again, this is my implementation. It doesn't matter. You can create your own implementation. It doesn't matter as long as the logic is same. All right. And at the very end, if single size is still greater than 0, I'll push back that single array. Now, in this segments array, I have now successfully bifurcated positives and negatives. Now, what will I do is, I will convert all the segments into positive. So I'll go into every array in the segments that's referencing IT, that's the array. Then every element in that array that's referencing I, and then I will convert I to be absolute of I. Why I have done this? Because of the mirror logic. I'll say that, all right, if you're standing at this position, then you can maybe convert this whole array to not look like this. Maybe you can convert it to look like this. And then calculate your answer. Same deal, it's a big deal, right? So I'll say, all right, convert everything to positive. And then for every segment, like as in every array in the segments array, 2D array, find for one array the answer and increment your answer. And this function is now what we can discuss. Long function takes an array. What is going to do? Taking the count initially starts with array 0, start an index from 1, and then calculate the difference of array of I minus array of I minus 1 and take it with max with 0. That means you only want the either it should be positive or it should be 0. It cannot go negative. And then you return the count. So I'll do this for all the segments and I will get the answer. All right. So I think this clears up more of our approach. Now let us try to discuss the time complexity and space complexity. So obviously over here you are running a for loop. So you can say this is order of n, right? And then you're running a n loop over here again. So this is again order of n. And then pushback is also going to take some time, but this pushback is not taking time of n into n. Don't consider that, because what is happening is once you have covered some segment, then you are pushing it back. So that's saying that I have iterated let's say I have iterated 5 numbers and then I push back those 5 numbers. So it's kind of saying that this, although it's going to take a worst case time complexity of n, you can say this is getting added, not getting multiplied. Same thing with clear. Clear function also runs in complexity of n. This is getting added, not multiplied. So eventually you can say that the complexity of this for loop is actually order of n only. I hope this clears, right? Now I'll say, all right, push backing the size, that's fine. Iterating in this segments array, again, the total size of segments array and every number in that will eventually club out to be the main array, because what you have done is you have bifurcated the main array into some segments. Total length of the segments will be n only, right? So can I say that when I iterate these two for loops, eventually I'm only iterating n times? And similarly over here, I'm iterating n times because inside this I'm going to one segment, but over here the iteration is done in array size, which is again this array size, which is that segment size. So eventually I'm calculating or iterating on the total length of all the segments. That's basically n only. So I know I have a n complexity only that is getting achieved. So I can say time complexity is order of n only, which is good to go because I'm in 10 power 5 order. And what about space? Again, I'm using a 2D segmented space, which you can say, and which is eventually saying that I'm storing all the segments. So I can say eventually the total length of the segments, that is n only, is the size of that 2D segments array. So you can say O of n is the space also in this. Now if you submit this, you will get an accepted solution. Hope so, I think. Yeah, getting an accepted solution. All right. So again, very, very descriptive and very like kind of an ad hoc problem also, I should say, in this case. I hope I was able to bifurcate the approach by the visualization. You can again obviously try to pause the video, create your own implementation to this, and come back to the main approach. And like, so takeaway from this problem is actually to this only, that hard problems sometimes maybe you can try to maybe look into what much more easier can I do, what much more easier can I do, and so on, so on, and then try to figure out the main problem. Kind of like how we do in DP, sub problems to problems, right? That is what we have done away. We created a sub problem for ourselves, which made sense because the difference was same. Then another sub problem that where we said let's only consider incrementations first, and then finally came to the main problem when we figured out, yeah, this happens, difference is same, incrementation, decrementation can be handled together, right? All right, so I hope you liked the video. Thank you for watching the PCD.